In the first problem, we're given an inductor and a capacitance, and the question is to find the frequency at which the two reactances are equal in magnitude. This has a reactance X sub L. This one has a reactance X sub C. Well, X sub L is equal to omega times L. X sub C is equal to 1 over omega sub C. So when these two things are equal to each other, when omega L equals 1 over omega C, then we have omega squared LC is equal to 1, or omega is equal to 1 over the square root of LC. So this is the frequency at which the two reactances would be equal to each other. Well, in terms of F, the cyclical frequency is equal to omega over 2 pi, which is equal to 1 over 2 pi square root of L times C. So now we substitute the values that were given in the problem. The inductance was 10 millihenries, that's 10 times 10 to the minus 3, and the capacitance is 0.2 microfarads. This becomes 0.2 times 10 to the minus 6. And when you do the calculation, you get for the answer that the frequency is equal to 3559 hertz. 3559 hertz. And so the answer would be part A, 3.56 kilohertz. Problem number 2, we have a voltage waveform which goes up to a value of 4 volts until pi over 2, drops to a value of 2 volts, stays there until pi, goes up to 4 again, stays there until 3 pi over 2, drops down again, and then levels off. Now this is a repeating waveform, and if we like, we can assume that this is a period to this point, or we can take advantage of the fact that we can also use this as a period, a waveform, because it's repeating itself. So let's do it either way, we'll get the same result. Let's assume that this is a period at this point. And if you take it out to the next level, you'll get the same result. Now, to find the effective value, or the RMS, we have to do 3 things. First, we need to square the waveform, find the mean value of the squared waveform, then find the square root of that mean. So let's start off by squaring it. 4 gives me a value of 16 in height, up to 16 volts squared. The part that's 2 goes up to 4 volts squared. So when I square this waveform, and I'm not going to bother the second half beyond this point, just take this first part over here. You can see now I have a rectangle here whose height is 16 volts squared, because I've squared it, whose width is pi over 2. So that's the area under this first rectangle. Now the second rectangle, remember now I squared this one also, I'm going to have 4 volts squared is the height, and the width is also pi over 2. So this represents the area of the second rectangle. This will be the total area when I add these together. I take the total area and I divide that by the distance from here to here, which is actually pi. So that the average over this distance, which I can call the period, would be given by what we're showing here. Now, if I were to, this of course will now be, I've squared it and I found a mean. That's the MS, the mean of the square. Notice that the pi will cancel this pi and this one over here. What I'm left with is the mean squared is equal to 16 over 2, which is 8, plus 4 over 2, which is equal to 2. I have a total of 10 volt squared. Now let's take the square root of that. The RMS would be the square root of 10 volts squared, which is equal to 3.16 volts. So the answer is 3.16 volts, which is answer D for problem number 2. Notice that if I had included this next part in continuing to find that, I would have doubled the area. I would have had 2 of these and 2 of these, but now I would have had twice as much distance here for a 2 pi along this axis. It would have made any difference. I got the same result.